this presentation, we are going to talk about alkaloids, which means alkali like. It is a name given to all the organic bases isolated from plants. Alkaloids are very poisonous but are used medicinally in small quantities. Alkaloids exclude amino acids, peptides, purines, amino sugars, and antibiotics. They are found in the seed, roots, leaves, bark of plants and generally occurs as salts of various plant acids like acetic acid, oxalic acid, citric acid, malic acid, tartric acid, and many more. Here in this presentation, we are going to talk about one of the alkaloid, quinine, its structure elucidation and synthesis. This is part 1, that is structure elucidation of alkaloid, which we are going to discuss in the forthcoming slide. Quinine is a cinchona alkaloid in which the hydrogen at the 6th position of the quinoline ring is substituted by methoxy group. It has a role as an anti-malarial drug, as a muscle relaxant, and as a non-narcotic analgesic. Pure quinine and cinchonine were first isolated in 1820 by Pelter and Cavendish. This is the process by which quinine is extracted from the bark of the cinchona plant, and we get it in a form which can further be studied and analyzed. Continuation of how the quinine is extracted from the cinchona plant, and quinine is obtained from the sulfate by precipitation with alkali, washing and drying, and now it is ready to be used for further study. This slide specifically shows the properties of quinine. It is a white crystalline powder. It is an antipyretic, analgesic, anti-inflammatory, antimalarial. It is insoluble in water. It melts at 177 degrees centigrade, and it is levorotatory in nature and has a very bitter taste. It is one of the 30 alkaloids found in cinchona bark, like rubene, quinine, quinidine, cinchonine, and cinchonidine. Quinine is one of them, and it is very important as medicinal plant. Its molecular formula is C20H24N2O2. The presence of two tertiary nitrogen atoms is confirmed as it adds 2 moles of methyl iodide to form diquaternary salt and confirms it as a ditertiary base. The presence of secondary alcoholic group in quinine is confirmed by 2 factors. It forms monoacetates and monobenzoates, which confirms the presence of OH group. And on oxidation, it gives a ketone, quinone, which confirms that it is a secondary alcoholic group. The presence of methoxyl group in quinine is confirmed by its reaction with HCl, which forms methyl iodide. And this confirms that the second oxygen atom in quinine is found to be present as a methoxy group. The presence of olefinic linkage in quinine is confirmed by addition of bromine and hydrogen in presence of catalyst platinum. It proves that quinine has an olefinic linkage, and further the addition of halogen substituted compound also confirms the presence of olefinic linkage. Presence of vinyl group in quinine is confirmed by its oxidation with KMNO4, which yields a monocarboxylic acid along with formic acid. This reaction reveals that vinyl group is present in quinine. The presence of quinoline nucleus in quinine is confirmed by its treatment with concentrated KOH, which yields a mixture of 6-methoxyquinoline and 4-methoxyquinoline along with other products. So this confirms that quinoline nucleus is present in quinine. Quinine on oxidation gives quininic acid, and on controlled oxidation gives meroquinine along with quininic acid. So these are the 2 products which we get on oxidation of quinine, and the complete structure of quinine can only be established when we establish the structure of these 2 components. In order to confirm the structure of quininic acid, it is first treated with soda lime, by which it undergoes decarboxylation to give 6-methoxyquinine. The position 6 of the methoxyl group has been confirmed by conversion of quininic acid to 6-hydroxyquinine by heating with hydrogen fluoride. When quininic acid is oxidized with chromic acid, we get pyridine 2,3,4 tricarboxylic acid, which is evident of the fact that benzene ring of the latter has the methoxy group is oxidized. The COH group at C4 reveals that in quininic acid, the COH group is present at 4 positions. The reaction is shown below. The reaction given over here shows that quininic acid is treated with HCl. We get a demethylated product, which shows that methoxy group in quininic acid is present in 6 positions. Now the structure of meroquinine, its molecular formula is C9H15NO2. It forms monosodium salts, which shows that one COH group is present. When it is reduced with hydrogen, it takes up one molecule of hydrogen, showing the presence of a double bond. The presence of double bond indicates that a CH double bond CH2 side chain is still present in meroquinine. When meroquinine is oxidized with cold acidified KMnO4, it gives chinchopleonic acid, a dicarboxylic acid and formic acid again. The formation of formic acid reveals the presence of vinyl group in the side chain of meroquinine. As meroquinine can be benzoylated, acetylated and nitrosated, it means secondary amino group is present in its structure. When chinchopleonic acid is oxidized with acid permanganate, it yields loeponic acid C7H11NO4. It is a dicarboxylic acid and contains one methylene group less than its precursor. It means that the latter contains at least a side chain which is CH2COOH. Loeponic acid has been somewhat less stable and isomerizes to its more stable form on treatment with KOH. Hence, loeponic acid should also be a piperidine 3,4-dicarboxylic acid, as is shown by the reaction over here. Loeponic acid contains one CH2 less than chinchopleonic acid. So chinchopleonic acid should be, the structure is shown over here in the diagrams. On heating with HCl, it produces 2,4-dimethylpyridine, and on heating with concentrated H2SO4, it gives gamma picoline. Meroquinine gives chinchopleonic acid along with formic acid on oxidation, so it should be either structure A or structure B. Structure A is found to be correct since meroquinine forms 3-ethyl-4-methylpyridine. Meroquinine on reduction with zinc and HI gives chincholopion, which has a carboxyl group and an ethyl group. So structure B cannot be accounted for the formation of this structure, so it should be structure A, which is more reliable. So now we know the structure of quininic acid and meroquinine, which are the oxidation products of quinine. Quinine does not contain COH group, showing that the two moieties are linked through those carbons. Quinine is a di-tertiary base, but meroquinine contains a secondary nitrogen and a COH group, showing that during oxidation, the tertiary nitrogen has changed into a secondary and a COH group is formed. This is possible only when the nitrogen atoms is a part of the condensed ring system like this. From the above facts, we can conclude that in quinine, the quinoline nucleus is joined at position 4 and in quinosilidine at position 8. The last thing to be fixed is the location of the secondary OH group. So Rave oxidized quinine to quinone by using chromium oxide. Quinone on treatment with amyl nitrate and HCl gave quininic acid and an oxime. This shows that methylene group is present adjacent to the carbonyl group, which is formed from CHOH group linking of the two moieties. This is the final structure of quinine which we have been able to elucidate throughout the presentation, and this structure is further confirmed by a synthesis which I will give in my next presentation. Thank you for your patience listening and going through all my slides on how to determine the structure of quinine, and this must be helpful in understanding a better way the structure of quinine. Thank you so much.